Okay. So paired sample t-test. So we talked about it when we talked about study design. We talked about two different main groups of design. We talked about the within groups design and the between groups design. So remember, between groups design, the most typical classical form that you could think of is a randomized controlled trial or a cohort study, which is basically the non-randomized version of it, where basically you have an individual during a baseline period, and then you follow this individual over a period of time. So that individual basically, then you have several individuals, and then you have two samples basically that you follow over time. What you do then essentially analytically, you compare these two groups in terms of their mean differences, or you compare them between the groups in terms of their means. If you have mean differences within one group, you have a within groups design. If you compare characteristics or statistics between the two groups, you have a between group design. In both cases, you have two samples. Not really true for the within groups design, because these two samples that you have are basically the same sample. It's the same sample in a before and an after condition. So there's some chronology to it. That means you're following them over time. So you have two time points where you assess your sample, and you're comparing these means before and after. With an independent sample t-test, you have two independent groups that you're comparing in terms of their means against each other. And that we will do on Monday. It's a little bit more involved arithmetically, and in terms of the calculation, they're a little bit more involved, but they're also not super difficult. Good. But today we're talking about the paired sample t-test. And what you do in the end of the day, you're comparing two means for within groups design. So you have that mean, that sample before, and that sample after. You use this for various studies, and one way how you basically would think of that, you can, what studies, for example, you would use if you follow a group of people in terms of weight loss. Yes. We're going over the midterm. That's difficult. So this is there's a lot of questions, right? Each of you had an independent quiz test. If you have specific questions about the question, please post them on the discussion board. Shoot me an email, and then let's have a conversation about this question. So usually the questions do have some response. So you should have the answers, the correct answers. So, but we cannot independently go over each question. So there are, if you have specific questions that you want to have explained in more detail, I'm happy to do that. But post them first on the discussion board, and then just raise your hand next class. We have Wednesday next week, we have a review session. So that's the perfect forum for having discussions about specific questions. Do you have a question already, or?
I have a question from my but I mean, I guess I'll just bring it up.
Let's do discussion board first, but please raise your hand. I missed a couple of you posting on the discussion board, and I apologize for that. I caught up this last weekend, and I'm sorry for not being responsive. I think it makes sense to give me a poke via email. So for some interesting reason, and was whenever I teach with Blackboard, it actually notifies me on my email. Canvas doesn't do that for some reason, so that's why I missed it. So sorry for that. Okay. But concerning the paired sample t-test, so it makes before and after comparison, and it's used in many study designs. Of note, in many randomized controlled trials, for example, you utilize a within groups design to basically transform this in a between groups design. So you calculate first the differences within the group, and you see there's no significant difference within the control group, and there is a significant difference in the intervention group, and then you compare the differences between those two groups. So that's where you kind of, it's a mixed bag. In real life, it becomes a mixed bag. It's not as black and white sometimes. So what you essentially do, yeah, this card example is not a good example, but what is a good example is this. Who of you has heard about the freshman 15? This is a thing, right? The other class told me the same. It is really a thing, apparently. And today we're going to find out if it really is a thing. I don't know, but we'll see. So what you essentially have, so when is it? It's you're coming to college and gain the weight during college, or you come back home at the end of the semester and gain the weight at home? It's in college. Okay, good. Okay. Okay. So if you gain those 15 pounds, let's see whether this is true or not. But basically what you have a before and after situation, right? So you come to college, that's your before. At the end of the college, you're coming back home, was more, same, or less weight. So, and this difference between before and after is what becomes your comparison distribution. And the way you have to look at this is essentially the same as if you would compare your sample mean to the population mean. But now the population mean in the single sample t-test is nothing else but the null hypothesis. So essentially what you are standardizing with the standard error of the mean, where you assume this distribution of sample means, the standardization process, you're standardizing your difference between your sample mean and your population mean. And now your population mean, which served in the single sample t-test as your null hypothesis value, because your null hypothesis said that the difference between your sample mean and the population mean was 0. That was your, welcome. The difference was 0. That's your null hypothesis. And now the null hypothesis is a little different because now you have before and after. And if you calculate the difference between before and after, and this is your comparison distribution, your null hypothesis is essentially a mean weight difference of 0. So that's your null hypothesis. And that makes it a little different, slightly different, because when you think of that as your comparison distribution, each of these points is one sample of, let's say, 20 students that came to college and then left at the end of the semester. Each of this point is a sample of 20 students. Each of the students contributed one difference, and each of these samples contributed one mean. So all of these are means. So this is the distribution of your sample difference means. I know this is a little complicated, but it will make more sense once you see it in Excel. And I want to jump right into Excel because it just makes it much easier to understand if you see it calculated. Oh, come on. Okay. So we have now, okay, that's the explanation. So we have freshman 15 refers to a supposed weight gain of 15 pounds or 7 kilograms. In the first year living away at university, one study found that male university students gained an average of 3.5 pounds between the beginning and the fourth semester in November, and female students gained an average of 4 pounds. We can use a paired sample t-test before and after. And the way you have to look at this, so let's assume this is a sample of 1, 2, 3, 4, 5, 6, 7, 8, 9 students. So these 9 students were measured before and after. So your comparison distribution is the mean difference, the distribution of the mean differences, the mean sample differences. I keep on getting mixed up, and I want to make the distinction between different scores and mean sample differences, mean different samples. Not that I'm misspeaking. So you have before and after. These are individual students. These are individual scores. The very first thing in the paired sample t-test, you need to understand your population. You need to understand, okay, so that's a sample of 9 students. Came in August, September, came to university, left in November or December. You want to first understand your difference. That's the very first thing you need to do. And the difference is calculated by subtracting one versus the other. And now we're getting to a practical aspect of this. The practical aspect is you can hypothetically use this in the form that you subtract after from before, or you can subtract before from after. Both come to the same end, statistically, not conceptually. Because conceptually, you're doing yourself a favor if you subtract after from before, no, before from after. Because what you create when you do that, you create a positive value if it's increasing and a negative value when it's decreasing. And that sounds simple and it sounds absolutely unnecessary to even mention. But conceptually, it will make your life easier if you just embrace this as the general rule in questions like that. So there are some cases where you would do it differently, but it just makes it simpler to think of that way. So now you have and I would refer to this in data management and in data analytics as you collapsed two values to one, which is just an arithmetic difference between those two individual score, a list of scores. So now when you calculate now an average, so you have an average for the before value, and you do have an average for the after value. And there seems to be an increase from 71.67 to 72.22. Arithmetically, this is an increase of 0. So this minus this is now 0.56. 0.56, these 0.56, and this is also an important rule. Remember how to calculate averages arithmetically, because the difference between two means is equal to the mean of all differences. That's also, it's simple and something that may not even have to be mentioned, but I'm just mentioning it because it's some insights that should always be quite readily available. Okay, so again, the differences between two means before and after is equal to the average of each individual mean difference. So that gives us the average. So we know now our average. What do we need next? Again, our comparison distribution is, okay, let's do it formally. So step one is it's 9 students. So our n is n equals 9. What is the corresponding degrees of freedom? That's 8, right? So it's 9 minus 1. We have now, there is a change. So there's an increase change. The change is 0.56. And we have followed them from, let's say, August to September, or no, August to December. So that's the comparison distribution. The comparison distribution is the comparison of sample mean differences. So in step 2, and this is where we're going back, we determine a null and a research hypothesis. So now I kind of gave this away already. So we have an HO and HA, where we basically have now as our hypothesis under the null hypothesis, we think that the mean difference equals 0, right? So we're comparing whether this mean difference that we have quantified here is 0 or not. And so our mean D is unequal to 0. That's our null hypothesis. We're doing this as a two-sided test. Hypothetically, we could also do it as a one-sided test, and we will discuss this, how to do that. So that's our step 2. What are we doing next? We determine the characteristic of the comparison distribution. So we have started doing that already. So we have calculated our average. And now next we want our standard deviation. STAT1021G. So we want to know how this distributes. So we have now a variation of 3 pounds around our mean of 0.56. There's a little subtlety. These variabilities, while the average is here, the differences between those two averages would be equal, as the difference between the two averages is the same as the average of the individual differences. This is not true for the standard deviation. The standard deviation may be very different between the individual scores and the differences, conceptually, right? Has to be. So don't rely on this being in any way comparable. Okay, but we want something else. So we want in step 3, not only the standard deviation, although it's important, the standard deviation we have right here. We want, in addition to that, we want our standard error of the mean. And we know how to calculate that. That's basically the standard deviation. 11 divided by the square root of our degrees of freedom, and that's 8. And our standard error of the mean is now 1.06. So now we know already that's simple from now on, right? So what we also need to define, and this is also listed here, so we determine the critical values or the cutoffs. And that can easily be done, as we know already. So the critical values is now, we have with a degree of freedom of 8, our critical value is, and this is where we consult the t-distribution table, with a degree of freedom of 8. Again, make sure that you memorize how to read the t-score table. You have the degrees of freedom here as the first column. You have one-tailed or two-tailed here on the upper 2 rows. If you go for a two-tailed 5% alpha, you basically finding with a degree of freedom a corresponding t of 2.31. Adding this now here will basically allow for you to also, since we can do that already, we can also calculate the scores. So if we say 95% confidence interval, we can calculate the lower limit and the upper limit. And so we know the 95% confidence interval is calculated as the mean minus the critical value multiplied by the standard error of the mean. So we have our mean of 0.56 minus 2.31 multiplied by standard error of the mean. That's minus 1.8 or minus 1.9. Well, the upper limit equals 0.56 plus 2.31 multiplied by the standard error of the mean. And that's 3.01. So what can we say already about this hypothesis test that we're about to do? We know the critical values, we know the thresholds, and we see in comparison to that our critical mean, we see already it's not significantly different, because our null hypothesis is contained, our null hypothesized value, reference value, is contained within the upper and the lower limit of the 95% confidence interval. Consequently, this cannot be significant. Good. But the way you're calculating this, I just want to bless you. So I just want to carry this over. This is the next example already. I just want to show you this. Bless you. I just want to show you this. So this is now the mean difference, the m minus 0 divided by SEM. And there's a reason why I'm showing you this. So this is basically our mean difference. I want to put the subscript. Hold on, how do I do this? Text effects. Sorry, just how can I make the subscript? Okay, I failed to make this subscript. Sorry for that. So basically, the calculation of the mean here is our mean difference, 0.56, minus our null hypothesis, divided by the standard error of the mean of the differences. What would you think? So now I'm coming back to the within groups design. So if you had a null hypothesis value that is not 0, the only thing you would need to do is to replace the 0 by the null hypothesized value. That means, for example, if you're facing a question that is, okay, so I'm trying to test whether a group of toddlers from year 1 to year 3 showed an increase in weight exceeding that of the average population, which is, let's say, 1.2 pounds. You would replace your 0 here with 1.2, because this becomes your null hypothesis in this context. But back to the freshman 15, let's assume that there was no weight gain during that period in university during the first year. And that seems to be correct based on this null hypothesis. So we're calculating now our difference minus 0 divided by our standard error of the mean. Well, let's actually do that. It's different. So now our t here is 0.52. So we defined the critical value of 2.31. Our t is not exceeding 2.31. What would it look like if that were a one-tailed hypothesis? You would need to keep in mind whether you are hypothesizing an increase or a decrease. So if you do a one-tailed hypothesis, and you're saying under the null hypothesis, you're saying your mean d will be smaller or equal than 0, and your mean d under the research hypothesis would be greater than 0. Then you're essentially looking at, you're interested under the null hypothesis, everything below your mean difference, and under the research hypothesis, everything above the null hypothesis, above the calculated t. So remember, always remember, no, come on, that's it. Always remember this slide. It's still my favorite slide in that regard. Do you remember the cholesterol example? when you have the cholesterol example, you have here a one-tailed, one-sided test that basically tests the null hypothesis that mu is smaller than our population mean. So that's the directional test. And the research hypothesis is that it's greater than that value. If you're hypothesizing under the alternative hypothesis that it's greater, you're interested in everything above that. So this area under the curve above your calculated t is basically giving you the probability of this being significantly different from under the research hypothesis. Whereas when you have the null hypothesis phrased in a way that it's greater equal than a certain value, reference value, so this would be 0 for the paired sample t-test. It's the same depiction, same concept, but the null hypothesis would be different. Under the research hypothesis here, it's that the mean is, it would be mean difference for the paired sample t-test is smaller than that reference value. That would be 0 in our case. Then you're interested in everything below. So in our example here, we are basically interested in everything greater than 0, or everything greater than the calculated t. So we're basically interested in everything above. So under our, that's why we would here assume this is a positive and a one-tailed hypothesis with 5%. Our critical t here would be 1.86, positive 1.86, notably. So we are assuming now our critical value is now, critical t is 1.86. And we have calculated, and the calculation for a one-tailed test is the same as it was for the two-tailed test. So we're again deriving a t-score of 0.52. So it's the same value. So also under one-tailed hypothesis, we're not rejecting the null hypothesis. So we're accepting 0, H0. So we're accepting the null hypothesis and rejecting the alternative hypothesis. So that's basically how easy that is. So this is our step 6. It's simple, right? It's not complicated. And this is of all the tests, probably the most simple statistical test that we're going to do now in the second half of the semester. But it's also, to be honest, for the real world, it's the most common used one. You will find the paired sample t-test. Yeah, in most studies, there's a paired sample. In many studies, it's paired sample t-test involved in some shape or form. So independent sample t-test and paired sample t-test is like this. This is like the most popular tests you will find in research. Okay. So this is basically that example. Are there any questions concerning this? I think it's considerably easy and it's not overly complicated. We will do a little bit more examples. And but again, keep in mind, we are basically working. Oh wait, last thing. So you remember that for the SET test, it was kind of complicated, and you needed to go in the t-distribution table to find the exact percentage. So the t-score table is not really structured like that. It's not really easy that you find out what percentage corresponds now with this. Well, you know, from the critical value, you know it's either 5% or 2.5. But basically, when you get a value of a t-score like we did 0.52, it's not really easy to quantify what's the actual p-value. So there is a function, Excel function that you can utilize for that. And I just want to spend a minute to explain that to you. It's actually pretty useful and very simple function. So the way you would do that, and I do this with the two-tailed hypothesis. Let's not go too deep into one-tailed hypothesis here. Oops. We want to know now our p-value. The way you would do that is with t-test. And I just want to show you this with the formula builder. So you have on the left top, you can click on the formula builder. And this is where you define what you're actually comparing. So if you have array 1, you can go on array 2. Bless you. The tail is, if it's one-tailed or two-tailed hypothesis, the tails are 2. And then it asks you here lastly for the type. So you can't see it, but you can see it if you open the formula builder. So it asks you for, if you have a paired sample t-test, it's 1. If you're two sampled equal variance homoscedastic is 2. And the two sample unequal variance, it's a 3. So we're not going to talk now about the two sample t-test. That's the independent sample t-test. We're typing in 1. And this will give us here the corresponding p-value. And the corresponding p-value is here 0.59. And this is basically the p-value under the null hypothesis. So this is the leftover. No, that's not a good depiction. This is a better depiction. So what you basically have here is that this is a two-tailed test. You basically get a value that is somewhere here. 0.52 is somewhere here. So the leftover probability that this is not different is basically everything from here to here. That's your leftover p. That's the probability that this is not significantly different from. So it's greater than 50% because it takes minus 2.5% on the left, and then it goes all the way to 0.52. And that would be the way how you derive that. But this is the calculation that is here computed by Excel. So t-test, very, very useful function. And as you can imagine, what you would do in real life, right? So you wouldn't. Also, to be fair and honest about it, a t-score table is not something that you really use when you do data analytics somewhere out there in the research institute, right? So this is, you're doing this now basically because you're studying it and you need to understand the concept, but it's basically, it's not something that you would do. You would use Excel to do these tabulations. Okay. Okay, but when it comes to the freshman 15 and our example, so you basically, your comparison distribution is the differences, and each of these mean differences, that is our sample. That's the sample, the 9 people that we have. Each of these samples is one of these squares. So now we're doing another example. Any questions of that on that? I think it's considerably simple. So basically you get that difference and you hypothesize under the null hypothesis that this difference is equal to 0. And then you hypothesis test it against that value of 0 or any other reference value if there's one implied by the question, which you may see on the exams. And we can also do examples on that. So essentially, you're standardizing then the difference of the mean difference versus that null hypothesis difference. You're standardizing it with standard error of the mean derived from your mean differences, or from your from the average divided by the sample size square rooted as the standard error of the mean. And the standard error of the mean is the variability of these sample means. So that's your comparison distribution. Good. Okay, psychology researchers hypothesize that when mental illness is suggested as the cause of a violent act, people pay particular attention to that suggestion, and it's important even inflates over time. So the idea here is that somebody reads a newspaper article and people will remember it more vividly if it's violent act in combination with mental health. If that is followed over time and you ask the same reader of that newspaper article again a week later, he or she will more likely remember that a week later if it was the combination between mental health and violent act. Whereas when it's only violent act, you will not remember it because, well, you will also remember it with some probability, but you're more likely to remember it if mental health was included, which is a psychology study that basically emphasizes mental health and the awareness of mental health as a potential cause of violent acts. We'll see the exact example. What they actually saying at the end. This report. So a news report about mental health of people who commit violent acts can contribute to widespread beliefs that people suffering from a severe mental illness, such as schizophrenia, tend to be violent. So there's a prejudice towards people with schizophrenia, and it's assumed that they're more likely to be violent. So psychology researchers hypothesized then that when mental illness is suggested as the cause of a violent act, people pay particular attention to the suggestion, and its importance even inflates over time. When no cause is indicated, we draw out existing beliefs, which often includes the stereotype that people with mental illnesses are violent. So we have here a sample, and this sample that you're looking at here is the probability of remembering. So that's the proportions of memory. And we're comparing this before and after. It's not my favorite example, to be honest. But basically, we are going step by step. So we have population 1, so that's mean 1, is people recalling details of the newspaper article just after reading it. Then they're followed over time. And then it's people recalling the details of the article 1 week after reading it. And we are again comparing this against the distribution of mean difference scores. Again, we have mean difference scores of 5 people. And we're comparing this before and after. Notably, we didn't talk before about the assumptions. There are also that's the same assumptions applied and did for the single sample t-test. We need to know that the independent variable is time. So this is time point 0 and time point 1 week later. So that's before and after, same thing, which is scale. Dependent variable is time, which is scale. In that context, it's actually not scale. Usually it's scale. If you use it as time here in this discretized, it's actually discretized. Participants were not randomly selected, so we must be cautious in respect to generalizability. So this is also, it's a random sample. Random sampling is the next assumption of t-distribution sample comparison, and we do not know whether the population is normally distributed. So yeah. So these are basically, we're not sure whether these are normally distributed. We don't know, and we assume it's not randomly sampled, and likely it is biased. And well, that makes it complicated. So what we first do, so step 1, we know in step 1 now that this is a sample of 5 people. Before is after reading, and after is 1 week later. Then we have under step 2, we're null hypothesizing. So HO is our mean difference, MD. Now I want to make this. Why is this not possible in format cells? No. Subscript. Yeah, MD. Okay, once you start something, you can stop it. Okay, MD, our mean difference is now equal to 0 in the null hypothesis, whereas in the research hypothesis, it's basically MD is unequal to 0. So that's our hypothesis. Step 3 is now logically we have to determine the characteristics of the comparison distribution. So now we're basically calculating an average of before. So that's A3 to A7. So now if we calculate the differences, that's now after minus before. And basically gives us here an average of 0.2, which is consistent with the difference between after minus before. Next, we need to calculate the standard deviation. And that's basically done with STDEF of these 5 entries. We're getting now an average, and an SD gives us here 2 different values. So we know now that the mean difference, the MD equals this, the SD equals this, and the standard error of the mean. So we know that N equals 5, and our DF is 4. It's 5 minus 1. So we know that the standard error of the mean is now divided by square root of 5. Step 4 is now to determine the critical value. This is done in the distribution table. If we have a T distribution table, we have a degree of freedom of 4. We're testing a two-tailed hypothesis of 5%, 5% alpha. Our critical T is 2.78. So 2.78 with 2.78, an alpha of 5%. So then last but not least, we're gonna do the actual test. I just want to bring this formula back. So our T is now the mean difference minus 0 divided by the standard error of the mean. So our T here is 3.16, which we see is significantly different from 2.78. So we know now that our difference of 0.2 is significantly different from our null hypothesis 0. And in step 6, we're rejecting now the null hypothesis. Okay, simple. It's really not complicated. And then it's just 95% confidence interval. That is basically just a calculation of lower limit and upper limit. That is basically the mean difference. It's basically the mean difference minus the critical value multiplied by the standard error of the mean. And equally, it's for the upper limit, it's the mean difference plus the critical value multiplied by the standard error of the mean. This is 0.376. So what we can conclude from that is just in line with the t-score that is greater than the critical value, is that lower limit and upper limit does not contain the 0 and confirms our rejection of the null hypothesis. Then lastly, we can also calculate the effect size, which diminishes the effect of the sample size because we're dividing now the difference by standard deviation rather than standard error of the mean, where the standard error of the mean is affected by the sample size, but the standard deviation is not. So we're calculating again, we're calculating mean difference of 0.2 minus 0 divided by our standard deviation of 0.14. We have an effect size of 1.4, which is consistent with a large effect size. Simple, right? So that's all to be known for the paired sample t-test. So I have two more examples, but I thought we're going to carry on first with the material. Thank you. Yeah, the constant draft kind of makes you sneeze. Okay, so we have, this is the example, 2.78, we're exceeding our critical value. So it's 3.17. We're rejecting the null hypothesis. We also went beyond the hypothesis testing by characterizing the variability in our actual samples, was calculating the confidence intervals. Noren and Heinzen also show here how to basically indicate that, but we know that it's like we have 2.5% to be considered in each tail, gives us to an alpha of 5%, adds us up to the 95% confidence interval. In this very same context, if you were to calculate now a 90% CI, and please make sure that you know how to do that in case it comes your way again. So if you have a 90% CI, you're using different critical thresholds, right? So if you have a critical value, if you set that critical value for an alpha of 10%, you have a 90% CI, and that critical value here is now for the same size, it's 2.13. Because what happens now is you're going further out. No, you're going narrower, further out with the 99%. Yeah. And so you're narrowing down your selection. So 2.13. You have G11, that's your mean difference. Let's calculate here. So we have the mean minus 2.13 multiplied by the standard error of the mean. And we have the upper limit is now the mean plus 2.13 multiplied by the standard error of the mean. So you have 0.07 to 0.33. So that gives you a wider, no, it gives you a narrower, and I'll say it again, gives you a narrower standard error of the mean. And thereby, it gives you a more stricter criterion. So, the effect size we calculated as well as 1.42. That's a large effect size. And then there's something else that needs to be considered. So we talked before about between groups design and within groups design. So if you have two groups and you're studying two independent groups of people, and you have a within groups design where you have a before and after condition. Let's say, remember the weight loss, no, not weight loss, the example of the wellness program, where individuals are enrolled in either receiving a wellness program or not receiving a wellness program. Let's assume you have a scenario where you have no wellness program and then wellness program. And then you have another group where you do wellness program and then no wellness program. So whenever you sense, or whenever the design implies that there may be what is called a carryover effect from the preceding period into the next period, you need to be very cautious within groups design, because this carryover effect will actually make the difference and this effect that your intervention may show less prominent. So it may render your significant intervention or your significant difference that you may have seen with your intervention a non-significant difference, and basically may render your study a type 2 error study. No, actually not even a type 2 error, because that would be sample size only, but you're reducing your statistical power based on your comparison. So this order effect is extremely important to keep in mind in all studies that use a within groups design. So basically, as soon as the order in which an intervention or the independent variable is basically applied changes the behavior, changes the dependent variable, you basically need to be considering order effects. So that's basically this carryover effect in the second period. So that logically will, let's say for the freshman 15, it could be something like the before and after. And then you test again after being at home for like a month, but at home they only got pizza. It's something like that, right? It's like it could be, if this changes behavior in the follow-up period, your differences may not be considered realistic. So basically, it's affected by the preceding period. And the way you would avoid that and mitigate this adverse effect on your study design is by counterbalancing. So let's assume you want to compare the changes within the changes between the college time and the at-home time. And that's your before and after. And you have now in college, the student developed a love for pizza and is only pizza now in the following period. The way to do this would be to analytically or by design change the order in which the patient either the subject, the student, is either first at home or is then in college. So you would basically shift that observation period. Another way in the wellness program example would be, for example, if you have an individual can either start with the wellness program first and then go in a no wellness program situation, or could be you split the group in half and you have the other half have the no wellness program period first. Thereby you balance this effect out and you see whether there's still an effect, even though you may have an order effect. So you're trying to kind of create a balance of individuals having one period first and the other period first for the second group. This is counterbalancing. Does that make sense? So you basically have condition 1, condition 2, and for the second group, you split that all in half, and then you have condition 2, condition 1. So you basically, by that, you create a crossover design. And that's how you can mitigate the effect of an order effect. Make sense? Do you wanna? Examples. Another example is like everything was weight is a good example, for example, or everything that affects. So if you have somebody exercise and you observe happiness during an exercise period and a non-exercise period, and that individual is exercising a lot during the first period, it's very unlikely that he or she may have been exercising a lot and then during the second period just stops exercising. So to take this effect out, you basically you create 2 equal parts of your study population, and you have first the exercise period and then the no exercise period. That's one way. And you have a second group then starting with the no exercise period and then moving into the exercise period to get the true effect of your intervention without the order effect. And this counterbalancing, the assignment of which individual then starts in which group first can also be randomized, and there would be a so-called randomized crossover design, which is a quite commonly found and quite commonly utilized design. Okay, that's it. Any questions? That was all for paired sample t-test conceptually. But we're gonna do these 2 examples quickly. I do have some more examples to resort to. You will also have paired sample t-test on your next homework, which are fun examples, and I really encourage you to do those diligently. It's always good to do these calculations yourself. I know with some of you may not be as experienced in Excel, but I think it's worthwhile the learning curve to really put time into this and to practice a little bit in Excel. Okay, and this is important now for midterm versus final in our case. What is 412? It's not posted yet. Don't worry. So, but good question. I think it posts on 3/29, and then you have 2 weeks to finalize it. Okay, so we have 2 exams. We have exam 1 and exam 2, and this is the kind of analysis that I essentially am looking at when I do the wrap-up analysis of whatever I give you and administer to you as midterm exams or quizzes. I want to know whether there was an overall change in the population. And basically, you're basically looking at the scores for exam 1, exam 2. The same concept applies. So you treat this as a scale normally distributed variable. Same concept. So you have differences. You calculate exam 2 minus exam 1, assuming that exam 2 is after, exam 1 is before. You calculate the averages. You calculate the average. You calculate the average difference. You calculate the paired sample t-statistics for these exam scores. So we know that there's one population that's 1, 2, 3, 3, 4, 5, 6, 8 individuals. So n equals 8. It's a group of students. Degrees of freedom are then 7. What is it? 8, 3, 6, 8. Degrees of freedom. Remember, degrees of freedom are always the n minus 1. Sure. So we have an average. So this is our m. Our m is this. Our SD is this. We're calculating the standard. The standard deviation of our differences. We're calculating standard error of the mean, which is the standard deviation divided by square root of the sample size. Gets us as standard error of the mean of 2 with an alpha of 5%. We basically get a critical T of, so degree of freedom is 7. 5% gets us 2.36. So our critical T is 2.36. What else do we need? We need the null hypothesis within H0, which is basically our M equals 0. Our HA is M does not equal 0. And then all we need to do is to calculate our M minus 0 divided by the standard error of the mean. So that's our critical, oops, that's our T. We see already it doesn't exceed our critical T, therefore we will accept the null. And then we can just quickly also calculate the 95% CI. That's basically lower limit, upper limit, same concept as before. We're calculating our mean minus our critical T multiplied by our standard error of the mean. Gets us minus 3.49. Upper limit is now 1.25 plus critical T multiplied by our standard error of the mean, 5.99. So that's our 95% CI. Now we have an effect size where we calculate our mean minus 0 divided by our standard deviation. Effect size of 0.22 is now essentially a small effect size, as we know. So that's how simple it is. The paired sample t-test is really quickly calculated. If we were using a two-tiered alpha level critical T, assume you instead collected exam scores of 1,000 students whose mean difference scores and standard deviation were exactly the same as for these 8 students, using a two-tailed test and alpha level of 0.05, identify the critical T values, make a decision regarding the null hypothesis. So if you have 1,000 students, and this is where it's getting interesting. So the T distribution, remember, the larger the sample size, the more likely it resembles, the more it resembles the normal distribution. So if you go up and all the way down, and you come to 500, your T distribution, your critical value for the T distribution is identical to that of the set distribution. And remember that this increasing resemblance is was kind of accepted with statisticians to employ as a concept once you have a sample size greater than 30. So you get away with your critical values of 1.96 already with a sample size of 30. But the higher the value becomes, the greater the sample size becomes. You essentially with 1.96, you already kind of, you really have a normal distribution that distributes in the same way, and you can use the same critical values. So now the sample size of 1000 has now a degree of freedom of 999. Your critical value here is 1.96. However, even though this was the case, you're still rejecting the 0. So this is your example C. So how did the sample size affect the decision? Question D, did not affect decision, change critical value. So this is the effect that sample size has, right? Because sample size, remember, sample size will narrow your variability, and it will allow for you, so the variability, notably the variability of your sample mean sample mean differences, the sample of the mean differences. Yeah. So you basically, you get, now you don't get, you get more accurate estimates of that actually true population mean difference. So there will be less variability in your estimates. So they will give you a true representation of what that mean is. Thereby, the standard error of the mean is smaller. Hold on. Sorry. The critical value changes the standard error of the mean. That was the keyword. It's actually a standard error of the mean is standard deviation divided by square root of 1000, and gets you a standard error of the mean of 0.17. And now your t is actually, forgive me, your t is actually to be calculated now as mean minus 0 divided by the standard error of the mean. And now the t is actually so. Okay. We're changing this. So now we're rejecting the null hypothesis. And we have now a large effect size. The critical value remains 1.96. 1.96 according to what I just explained before. All right, we're ready. Oh, 6:15. All right, good. Thank you very much. Have a nice evening. Any questions? That is the final result. Don't listen to the version before. All right, thanks so much. Yes.
First of all, I came in a couple minutes late, so.
Yeah. Yes, I can change.